Last session of the afternoon, as you know, in our original program, we had Yakir Aronov scheduled to give this talk. Unfortunately, due to his wife's health, he was unable to make it. That was, for us as conference organizers, 10 days before the conference. Of course, that was very bad news. But it was to a considerable extent offset by some very good news, which is that Sandu Popescu, who had previously told us that he'd be unable to attend the conference, had discovered that he was able to attend after all and has been kind enough to come to Cambridge to be with us and to present Yakir Aronov's talk for us. And so I'm delighted to introduce Sandu, whom I've had the pleasure of meeting for the first time here. And I'm also delighted to note that there's a very significant anniversary that we can consider ourselves to be marking on this day in particular on the conference, since we've been focusing so much on the ideas that go back to the famous ABL paper of 1964. And Matt tells me that we're within 2 weeks of precisely the 50th anniversary of that paper. So you could think of this as ABL after 50 years. Sandu.
Thank you very much. Well, thank you, and as customary, I want to thank the organizers very much for inviting Yakir. I also want to thank very much Yakir for not coming. And this gives me an opportunity to talk. But actually, to be honest, I was invited and I declined, but it so happened that I could be here. So, bad luck for you. Right. I'm supposed to give Yakir's talk, but Yakir always improvises, so I will try to improvise what he improvises. Also, Yakir always delivers his talk with chalk on the blackboard, which gave me the possibility to pretend that I'm doing this just to emulate Yakir and give you a feeling, not because I was lazy to prepare a PowerPoint presentation. So what I'm going to talk today is about a certain view of what time evolution is. And that is based on a paper that was initiated by Yakir, and we wrote it together with Jeff Tollaksen, that used to be here. He's still there. Okay. All right. So look, usually, the usual view of time evolution is that, well, I don't know, probably not the usual view in this audience, but the usual view in general is that you have a system and that evolves and goes in time. And that's what it is. But if you go back to antiquity, Heraclite, the view is that the universe gets recreated every new moment of time. You never bath in the same water twice. So every moment of time is a new universe. And somehow the time evolution is due to correlations between these various universes. So that is the thing that I would like to try and bring that view of time evolution to quantum mechanics. Okay. So just to start with, let me start with classical physics. And let me start with a much simpler question. And here it is. Suppose I have a particle. This is just to prepare for what is coming. So I have a particle here is time, here is position, and the particle just, do you see that in the back?
Yeah. No.
Okay, the particle just evolves in time. So now I ask, look, instead of one particle evolving in time, what I would like at a single instance of time to have n particles. And if I'm interested, where is the particle at some moment ti, I would like to make a measurement on particle number I that will tell me the position. So okay, that is pretty simple. What I do, there is no time here, but there is the label, the number of particles, particle 1, particle 2, particle I, particle N, and I would have here some positions of these particles. So essentially, if I want to know where is the particle, this single particle, at moment Ti, I go at particle I and look at its position. And that is all, and it's very simple and it is very trivial. So now I would like to do exactly the same thing, but for quantum particles. All right. So for simplicity, let me take the simplest quantum particle, that is just a spin-half particle, and let's take the simplest time evolution, that nothing happens to it. The Hamiltonian is 0, there is no magnetic field whatsoever. So if I look at the time evolution of this thing, this is time, the particle, suppose I start with it polarized up Z, well, the particle, not the best. The particle always remains polarized.
Oh, on the right there is another board maybe.
Yeah, let me try.
No. If you move it.
Yes, Liv. What was the suggestion?
If you move it, there is a white.
A whiteboard. Now let me try the blackboards if they work. There are more. If not, okay. So this. Where is the pen? There should be a marker somewhere, which I was not. Yeah, okay. All right. So there is no Hamiltonian, this is time, and I have a particle that is polarized up Z. And it stays up Z at all times. Instead of that, I would like now to put n particles, n spin-half particles, so that when I would like to know what is the state of this particle at time Ti, I will come here at particle I and measure it. It's a simple trivial thing. Well, I have n particles, particle 1, particle 2, particle 3, and so on. All of them are polarized with a spin up in the Z direction. Particle I, particle N, and so on. So you would think that this is the way to represent a single particle that moves in time by n particle at one given time. Well, if that would be the case, there would be no interesting talk today. And the point is that that is not a good representation for the time evolution of a single particle. Okay, let's see why. Well, there are a couple of reasons. First of all, is that this state contains far more information than this state. You see, suppose here I said a particle is upset. Suppose I wouldn't tell you what the state is. I just prepare it and I give it to you. Here you have a single particle. Now you have no way to determine with certainty what the state is. You could make some measurement, whatever direction, you don't know because you don't know what the particle was. All you can say is that it was not the opposite to the direction that you measured and you saw it. On the other hand, here you have n particles, all of them in the same state. So even if I didn't tell you what the state is, you start on some of them you measure x, on some of them you measure y, on some of them you measure z, you accumulate the statistics, and you start determining what the state is. And if I give you more points, that is more particles here, you can determine the state better and better. So clearly, this one has far more information than a single particle propagating with time. Okay. That is reason number one. There's reason number two, which is even more subtle than this. And that is, on this particle that is polarized upz, there are other things that I know with certainty about the particle. One thing is that the particle is upz. Now, of course, you would think that this is the only thing I know with certainty, because I don't know what the spin in the x direction is, or in any other direction other than z. However, I know something. I know that although the spin in the x direction at, say, a time t1 is completely unknown, it will be the same as the spin in the z direction at some other time, like, say, t7. So if I were to measure sigma x at t7 minus sigma x at t1, I should get 0 with certainty. Why is that? Because there is no magnetic field on this particle. So the spin in the x direction doesn't move. And in fact, none of the spin components move in this case. Incidentally, there is a very nice way in which you can measure. This is a two-time observable. It's the spin at t1 minus the spin at t7. Now, the trivial way is measure the spin in the x direction of t1, and then measure the spin in the x direction at t7, and see that it didn't change. That would be a bit too much. That would not only show you that the difference is 0, that would in fact tell you what the spin is, and you will disturb the state. But there is actually a very interesting way in which you can measure this two-time observable without disturbing the incoming state. And let me show that for you. Okay, I wanted to use the other blackboard, but something to erase. Okay. Fortunately, Avi didn't write too much.
I knew it was a wave coming from the future.
Ah, all right. So let's suppose that I have, here's what I would like to do. Suppose I have my spin, say, in the state up z, and I have a measuring device. This measuring device has a pointer q. Q is the location of my pointer, say 0 at the beginning. And what I do, at time t1, I want this to remain up z, and just move the pointer one step towards 1. So now the pointer is localized at q equal 1. On the other hand, if the spin was down z, at time t1, I would like the spin to remain down and the pointer just move one step to the left, indicating that it's down. At time t7, I would like to do the opposite, because I would like to measure the spin at t1 minus the spin of t7. So if it is up on q at t7, I would like to go up q plus 1, and if it is down at 7 and q, this is at time t7, I would like to be down and q minus 1. So this shows me that wherever the pointer is, it moves towards plus 1, or if the spin was down, it moves towards -1. That is the measurement at T1. And here is a measurement at T7. Now, the catch is I will use the same measuring device at both times. Not two independent ones, but the same one. So here it's now something interesting. Suppose the spin was in some arbitrary state, alpha up z plus beta down z, and I start with a measuring device at Q. At time t1, they get entangled. Alpha up z, Q minus 1, plus beta down z, Q plus 1. Now comes time t7. It is linear alpha. When it is up, it adds a 1. So this remains up z. And this is Q plus beta down z, again Q, which is nothing than the original state, alpha up z plus beta down z, Q. So what did I obtain? I see that my measuring device moved with a value 0. It was not shifted, telling me that the difference between the spin at the two times is 0. Had there been some time evolution between the time t1 and t7, for example, a magnetic field along the z direction, and that is a nice one. If it is along z direction, and if I start polarized, even just in up z, sorry, I wanted to put it in the x components. What am I measuring? I want to measure the x, that is what I was telling here. So nobody is following. That is very good. I can then do whatever I want. And, all right. So it is the x. So even if I start with spin up z, which means an equal superposition of up x and down x, but if there is a magnetic field, then this up x will now rotate and will become a down x. And then these equations will be mixed up together and they will not compensate. I will not get q equals 0. So here it's an interesting thing. I was able to measure this observable, which is the difference between the x components at two different times. First of all, without knowing what the x component is. And second, without disturbing the state. I recover the same state, which was the unknown state that I started with. I recover it at the end. So generally, it is not appreciated that we may have not only one-time observables, but multi-time observables. And in this case, I have a two-time observable that commutes with a one-time observable. Okay, so here we had subtle correlations between the spins. Although the spin in x direction at t1 is completely undetermined, and the spin in the x direction of t7 is completely undetermined, they are correlated. They are in fact the same. Now come back to this thing. Here I have n spins, all of them that are polarized up z. There is no connection, no correlation whatsoever between the spin in the x direction of particle number 1 and that of particle number 7. There are no correlations whatsoever like that. So this is the second reason why representing one single quantum particle that propagates in time by, at a given time, by n particles, all of them in the same state, this is not the correct way to do. Now you may say, look, I understand about the information, but here about the measurement, we know that the measurement disturbs the things, so perhaps I didn't take that into account, so perhaps the correlation in x direction are not so important. Well, they are, because even if you don't measure them, but you just look at the Heisenberg equations of motion, you see that they tell you that the operator sigma x at T7 is identical to sigma x at T1. Yes, Lev?
I know that Yakir gives the best talks when he's interrupted.
Oh, of course, no. I was just commenting that you slowed down quite a lot. So I'm glad that you interrupt, yes.
You said that on the one thing that you can get much more information about the
about this
on
one,
the right,
then about that.
and then some other information about the left, but
Not some other, less. Far less information, because here,
but
if I'm not told what the state is, I'm not able to find it. While here I
I
am.
understand, but then you cannot find what is a magnetic field on the left. So the second part was just the opposite.
No, no.
You
I
cannot
tell. Well, look, the game is like this.
Give me ask a question.
Okay.
So I think if you could say that on the left you can know more, you can know about the magnetic field now with 0. So I think the natural thing is to consider the general situation when you don't know the spin and you don't know the magnetic field. Now these two pictures will be different, but it's not clear that you will get more information here, more information there. If your information about what is a magnetic field and the spin,
Yes.
both things are known.
No, that is a perfectly valid comment. It's completely irrelevant for here because that discusses a different game. Here the problem, as I stated, and gives me the opportunity to restate, is very precise. I have a well-known quantum time evolution. This is well-known. I only want to reinterpret it following the philosophical idea of every moment of time a new universe. And all I want to do is to find out whether it is possible or not to model this thing in that idea. And for the time being, I'm doing a simpler, I'm addressing a simpler question, namely, is it possible, like in classical physics, where I could, by n particles at a given time, I could simulate one particle at many times. When the time evolution is known, there are no questions about the time evolution. I just want to present that in this alternative way, and I find out that quantum mechanically that is impossible here. This is the game. There are other games that are interesting, but they are different.
One more disturbance. But the fact that sigma x that didn't change, it's just a statement about time evolution. If you say that you know it, why you make?
Because all I want to say is that here I can find that it doesn't change, but if this is to make a simulation of that, here I find that sigma x of this minus sigma x of that is not 0. That is all I said.
Okay.
So in that sense, this system of n particles, it's not doing the job. It's not doing the job of simulating the known evolution of this time. That's all. All right. So then what can we do? Number one is we can say, look, bad luck, or in fact, good luck. This shows that I really have to think of a time evolution as being a single universe and the particle moving and changing in all time. And I should forget that stupid thing that the universe gets recreated and all that the time evolution is are correlations between the different things. Okay. Fortunately, there is a way to do it. But that way to do it, no, okay, you can continue. But that way to do it is very interesting. And that goes like this. Okay. I'm taking my n spins. Here are my n spins. And I'm taking some ancillas, other spins that I put over here.
Sandu?
Yes.
Sorry, do you mind another interruption?
Oh, I love it.
Before we get to the interesting bit.
Yes.
In our classical thing, our states were probability distributions rather than the position state of something. It seems like we'd end up saying very similar things. So n independent probability distributions would not be a good simulation.
Indeed.
What
But there would
progressing through time.
correct. But there it would be pretty trivial to arrange for n correlated probability distributions. And this is precisely what I want to do here. But here will be different.
Okay.
And that is it. Here, if I just wanted, it's important to appreciate, if you have these n spins and you want measuring each of them to be with certainty of z, you cannot entangle them, there is nothing else you can do. Then put all of them in the of z. So it's not that putting all of them of z is just one possibility, is the only possibility that is consistent with the fact that I measure it at one time, I think with certainty of z. So this is the only solution that exists in quantum mechanics, and it doesn't work. Fortunately, there is another way to do it, but involves something more subtle. And it's like this. You pick n spins, and next to or between any two spins, you pick other n spins that are ancillas. I draw them like these black dots. I am interested that at some given time, and here is my time, if I perform measurements on my spins, on these white ones, to find whatever I would find there. I prepare, so I'm looking at this at time, let me call this, it's a time tau. Tau equals 0. It has no relation with that thing. At tau minus epsilon, I prepare my spins in the following way. I prepare this one in the state psi, which in this particular case, psi is opposite. The ancilla and the next one are prepared in a maximally entangled state. So this is psi. This, let me call it, is a singlet. And another singlet, and another singlet, another singlet. In fact, let me prepare them in a triplet, in up, up, plus, down, down. It's more symmetric. Let's call this state S. At a later time, here, I perform some other measurement on my spins and ancillas. I would perform a band measurement here, a band measurement here, a band measurement here, one here, and so on. At time t0, perform whatever measurement you want on the spins, not on the ancillas, only on the spins. For example, you want to measure what is the spin at time ti, t7 or whatever, t1, 2, 3, 4, you perform a measurement here of the spin. You want to find out what is the correlation in sigma x, you measure between t2 and t5, you perform a measurement of x here and a measurement of x there. Now, you will be successful to simulate by these n spins a single spin there, if and only if here at the measurement of the bell thing, you get in all cases this singlet state. So, if it so happened that you were lucky and you got the singlet, then I can prove, and it's very easy to see, that any measurement that you want to do at the intermediate steps, either of psi or of the correlation, gives you exactly what you want. So there is a way to prepare 4 times 0, but if you make a preparation, let me call a tau minus epsilon and a tau plus epsilon. So if I pre and post-select them, then at this intermediate time, I succeed to reproduce the time evolution of a single guy. Now, let's go and take a a more detailed look. There is a single one that contains the state psi, and it's the one that corresponds to the initial time period. All the others are just in standard states, in this singlet with their ancillas. So, this system of n spins and n ancillas does not contain more information about the state than you have here. It is a single particle in this state. You can see pretty easily that if I perform a measurement here of the spin in the z direction, that the state here in fact will be psi, because what we have here is in fact a teleportation. You have 2 particles that are entangled in a singlet, you perform a bell measurement later, and only if you are successful to get the one that doesn't need to be repaired, then this state in fact now propagates there, or it propagates here, or it propagates here, and then you check. To check for the correlation is very similar. It's just a chain of teleportations. So, let me see where I am. So this was just a toy model. I wanted to prepare the grounds for what I'm really interested in, and that is to really put many time slices and make correlations between them. Okay. In classical physics, because I have here n particles, if I were to do that, I would say, look, let me stack them one on top of the other. So I would have like these phase spaces that I put one on top of the other. And what happens, this is phase space number 1, phase space number 2, phase space number 3, or in fact just space. And here it's a particle, there is a particle, there is a particle, and they are just correlated, and that's all. Now I would like to come and do something here. So I would like to come and say, sort of stack all these particles one on top of the other. But first I really want to get rid of the ancillas. Okay, because here I have a little bit too much in this game. I have my spins and I have my ancillas. I want to get rid of it. Okay. Right, in order to do that, now the problem is that Elitzur wrote very little, but he wrote quite a lot. So I want to make a little detour and take you back to the ordinary pre and post selection, the one that we usually. What is that? Oh, that's very good. Thank you.
Hello?
Yes. Oh, thanks. It has the shape of a smartphone, but is actually much more robust technology. So let me take you back to the ordinary pre and post selection. So the idea is like this. Here it's time. At this moment I prepare in time a state psi. At a later moment I perform a measurement of some operator B, and which has different eigenstates. And suppose, like I measure an operator, say B, which has eigenstates phi 1, phi 2, phi n, with eigenvalues b1, b2, bn, and I'm only interested in cases where, for example, only b1 was obtained. So then I say I have here a pre and post-selected system, pre-selected in the state psi, and post-selected in the state phi. Let me call this phi 1, just phi. This happened at time t1, this happened at time t2. Now, as discussed here today, the physics for the time in between is influenced or determined both by psi and by phi. And that is pretty trivial. That's very easy to see. Let me give a simple example here. Suppose that there exists some non-zero Hamiltonian, a Hamiltonian H, and suppose that here I perform at time t a measurement of an observable A that has eigenstates A1 up to AN with eigenvalues A1 to AN. And suppose, for example, that you would like to ask what is the conditional probability to get at this measurement A equal AI, given the fact that I start with psi, and given the fact that the final measurement got the state phi. This equals. Well, the standard way is to say I propagate psi from t1 to t, and if I were to get AI, the probability for that would be, let me see, I have to start with psi, to propagate with u from t1 to t, and to take the scalar product on AI and take the absolute value squared. Once I got the state AI, here it will collapse, forget me left, it collapses for all practical purposes, and then it propagates. So I start with AI, I propagate from T to T2. Do you see that in the back? They are sleeping already. Okay, so this is not exactly what I want yet. This is the probability of getting the intermediate state AI, and then from the intermediate state, once it is done, to get the final one. But I want to condition on this particular final one, so I just need to normalize this thing. And I will have here sum over k phi u from t to t ak u t1 psi. This is a trivial formula in conditional probabilities. So the way to interpret it is you start with psi. As a matter of fact, it's a product of two absolute values, which is the absolute value of the product. So let me even simplify. So the usual way of doing it is to say, look, I propagate psi from t1 to t and take the scalar product with the AI. Then I propagate AI from t to t2, and I take the scalar product. And it's trivial, it's very easy to do it. Now, if you look more carefully, you see that actually you have to work very hard doing this thing. Because the normalization says, look, but I have to normalize. I start from psi, I could get any intermediate value ak, and then I have to propagate this ak to the final state. So even if I'm interested in the probability of a single one, I have to compute, if this A has n possibilities, I have to compute to solve the Schrödinger equation n times to propagate the intermediate state up. But there is a simpler way of doing that. You apply your unitary to psi, so to propagate it like this, and you apply the other unitary to phi, and you propagate it to the middle. And now you only solve two Schrödinger equations, one for psi, one for phi. The same thing here. Of course, you need to do the n scalar products, but at least you only solve one Schrödinger equation for here. So looking these two ways in time is far more economical, at least as far as computation is concerned. If you were to do a computation, run the software and compute things, it's much better to do it this way. So already we see that from the point of view of complexity, looking at things propagating two ways in time is better. So I would like, of course you can look at what happens here in many different ways, but I would like to introduce something that I call a two-time state, that it is psi at t1, phi at t2. This is not a scalar product. It's a state that lives. This belongs into a Hilbert space at t1, tensor a Hilbert space at t2. And this is a Hilbert space of ket vectors, and this is a Hilbert space of bra vectors. And I prefer from now on to look at this object. This is a state living in this tensor product of two Hilbert spaces. What is the advantage of doing that? Well, it has an advantage, because if I say this is a state that lives in this Hilbert space, the next question is, can I superpose them? Now that is an interesting thing. So then I asked, does it make any sense to talk about psi1, phi1 with an alpha plus beta phi2, psi2? That's this state. Now this obviously is not an ordinary pre and post selection, because by a pre and post selection ordinary you pre-select psi and you post-select phi. So you need to do something fancier. But first let me see what is the meaning of this thing. Well, what I would like, and here comes an interesting part. Let me look at this formula. AI, let me simplify. Let me just put, it's just pi I, the projector on the state I, just to simplify this. And here is pi k. Okay. So I have some operator, some projector, which is u pi u, that is sandwiched between psi and phi. In this case, what I would like to generalize that thing and to say, look, I have this state that is alpha phi 1 psi 1 plus beta phi 2 psi 2 absolute value squared. And what happens? Here you see how it goes. I have this state, and in this slot in the middle, I sandwich u pi u. So all I want is in this state here to sandwich this u pi r u. Of course, there are two different u's. U pi r u. And of course divide by the same thing, sum over k, where I place psi k. So I would say that I obtain a superposition of pre and post selections if this is the way in which I obtain my probability for the intermediate measurement. Okay? And the question is, how can I prepare this? And here is a way in which I can prepare this. Here is a nice way in which I can prepare this. I take my particle and I take an ancilla here. And I prepare it, which is my pre-selection, in the state, say, alpha psi 1 up for my ancilla plus beta psi 2 down for my ancilla. Then at a later time, here, I perform a measurement, say, of the state up, okay, the state up of the ancilla phi 1 plus down of the ancilla phi 2. Now, if I only perform measurements of observables on my particle, and I'm not touching the ancilla, if you ask what are the probabilities here, you will see that they give that thing over there. So, usually you think that when you trace over a system that is not of interest, which is the ancilla, then you get a density matrix. Here it's more subtle because the ancilla is taken out of the game, finally, by doing this. So this is an ordinary pre and post selection, but it's a pre and post selection of two particles. So the upshot is that effectively this thing will mean that I have a pre and post selection on my system, but which is some sort of entangled pre and post selection between its past and its future. I leave an exercise for you to prove that if I do this pre and post selection, my formulas go like that. So now I go back to my thing, and I realize that I can get rid of the ancilla, but then what I get entanglement between pre and post selections. Now there will be more particles and more times because I have that whole structure, but here is the upshot. So really, what I had here, let me come back, I had these two times, T1, T2 in this particular case. So I have a Hilbert space H1, a Hilbert space H2. This is of ket vector, this is of bra vectors, and my states are things that live in this. Now I will have more times and more particles and so on, and I will tell you what is the upshot. Remember what was the situation there, and I will tell you the situation again. There were these things. Here I prepared a singlet, there I prepared a singlet, then later I performed this post selection, and so on. Because of this post selection, in fact, I can get rid of the ancilla and just look at the state of my particles. In this particular case, if I look only at my particles, I find this thing. I should use a different color. These are not singlets, these are the times tau plus epsilon, tau minus epsilon, here, here. These are the times exactly like the two lines where I draw for psi and phi. This little one is preferred in psi. This one, actually via these two things, it's a teleportation of that state over here. They are simply maximally entangled. That is, I entangle the state going backwards in time here with the state going forward in time of the second particle. Then I have another entanglement here. Then I have another entanglement there. If I were to write this, I would say, look, I have, this would be a 2-time state for n particles. So particle number 1 at time t1 is in the state psi. Then I have, let's put, what's the best notation? Let me say I, this is for particle 2 at time, particle 1 of time. Let me call this tau 1 and tau 2, not to have epsilon. Tau 2, tau 1. This was at tau 1. This would be the state coming for particle 1 at tau 2. And this would be entangled with a state that's going forward in time, I of particle 2 at time tau 1. Then I will have, and sum over I. Then I would have a j here of particle 2 at time tau 2, that it is a bra entangled, because I take sum over j, with particle 3 at time tau 1, and so on. So this would be a 2-time state, because discuss about T1 and T2 of n particles. And you can now check if you measure, say, the spin here or the spin there, and if you started with psi as you wanted, you could check that the probability of finding up, finding down, finding correlation between x's, they work for this state. So now I reduce the problem to only my n spins. I no longer have the ancillas. The roles of the ancillas were just to ensure that I can entangle this one with that one. And I have this equation. And now I'm going to stack them one on top of the other. That is the last thing I do. So, here is how the time evolution looks. I look at each moment of time. Each moment of time would be like a little brick. And to each moment of time, I'm not associating only one Hilbert space. That would be correlated with the Hilbert space of the next one, and so on. But to each moment of time, I associate two Hilbert spaces. One here, and one there. This is a Hilbert space of cats. This is a Hilbert space of bras. Here is the next moment of time. Here is the next moment of time. Here the state is my state psi. These are like handles on these little bricks or Lego pieces that you put. At the initial time, I prepared my system in the state psi. And here I know what the state is because here is that I prepared it. At a later time, all I know is that this moment of time, nothing happens. What does it mean nothing happens? the state propagating backwards in time is fully correlated with the state propagating forward in time there.
With the sign inverted, or?
Sorry? Here I'm not putting spins, I'm putting the direction of propagation. Sorry, I have a single color. This now doesn't mean spin, means that, okay, let me put a double arrow. So this is the way in which the states propagate. This is a pre-selected, a post-selected state. A pre-selected, a post-selected state. So if you wish, now I have a single particle in a multi-time state. Psi at T1, I at T2, I at T1, sorry, it's still T1 from the moment T1. At time T2, I have another particle. I have another Hilbert space. Is this Hilbert space I, sum over I, then I have J, T2, T3, and so on. So this is the way in which the propagation occurs. And the Hilbert space, I have one Hilbert space here times one Hilbert space there. So I have the Hilbert space H1 cross H1, it corresponds to time T1, cross H2 cross H2 time T2, and so on. So I have a multi-time state. I have multi-Hilbert spaces. And it is beautiful, at least in my eyes. And it is beautiful for a number of reasons. Number one is that I put the state only at the time where I know that I prepared it. What do I know about this time? At this time I know that nothing happened to it. Nothing happened. I didn't measure, I didn't interfere with it. So here is ordinary time evolution, which in this particular case means do nothing. They are perfectly entangled. Okay. Let now, first of all, let me do this. Right. Okay. Suppose that I have a Hamiltonian. The time evolution is not 0. That what is happening? Well, it is still the case that the states are maximally entangled at the junction. But how are they entangled? You see, one of them is entangled with the other one a bit tilted. So, it is not I, but will be I, and here it's the infinitesimal u applied to I. This was T1, and that is T2. Sum over I. This is again a maximally entangled state between this and that, but the way in which the entanglement goes, it's a little bit skewed. Okay? As a matter of fact, you know all these things, because you can say, if nothing happens to a particle, here's the time evolution. I start with psi, and then I put identity. Nothing happens. And I can put this identity at time t1 times identity at time t2 times identity at time t3, and so on. And every identity operator is exactly sum over I. That is the identity operator. So in fact, I just did this trivial thing, but I interpreted it in a very nice way. And if I have unitaries, well, I put here infinitesimal unitary, that is that. Now, what about a measurement? Suppose at a later moment, I come and I want to perform a measurement here. I perform some measurement of some operator C that, and I found some eigenstate psi, or psi of that thing. Well, I know that from now on, actually, there is the state psi that will propagate from now on. And so, here they are maximally entangled. What is happening in the past? Well, this is like a post-selection for here. So here is the state psi that is propagating over there. What happened with the entanglement between these two times? Went away. They are now a direct product. It's not a sum over I. You see, this is an entanglement as you are not used with. Usually I use entanglement between two cats. This is an entanglement between a cat and a brown. It's the same thing. So now the state is just psi. So time evolution, unitary time evolution means entanglement between subsequent moments of time. Each moment of time has two handles, one connected to the past, one connected to the future. If you measure it, the entanglement is lost. You disconnect this space from that space, which is exactly what you know. Because if you ask something about here, you say, I don't care about the rest of the history. I only care about the initial state, so this state psi. And that's precisely what the disconnection does. Yes,
Maybe tiny comment. As you draw your boxes, you have a long time for your when they don't, and then you have a very short time between them.
Yeah.
And
well, there is no
your
short.
time evolution is just between them. So I think you don't, in this picture, you don't need different eyes because it will come automatically. They will just evolve inside.
No, I don't think of this as being a time. They are just time moments. There is nothing else. This space really has no meaning.
I understand, but then the picture maybe it's better.
You do a better picture. I don't know how to draw it with spaces that don't exist.
Big distance between them.
No, then I would think that this distance has any meaning. This is just an illustration. This is a time. There is nothing else. There are these moments of time. All I talk are about the states correlated. By the way, why do I disconnect it here? Because when I perform a measurement is like an uncertain time evolution. That is more or less what a measurement is, because it completely randomizes some of all the observables that do not commute with what is measured. So it is not like a Hamiltonian that produces a well-defined time evolution, but it's Now let me tell you fancier things that you can do with this. And that will be the end of it. Let me first do something that is not so fancy, but it already involves EPR and Ellison Bob and whatever. So, how do I see a nice EPR? Well, in a nice EPR I have two particles. And here is particle on Ellison's side. And here is the time evolution of the particle on both sides. What do I know about the initial time? Well, at the initial time, they are entangled. So the state that propagates here forward in time is entangled with the state that propagates here forward in time. After it, each of them just has its own undisturbed time evolution. These, recall, are not directions of spins, they are direction propagating in time. So this is the image of an EPR. If this state is the singlet, and then each particle evolves in time very nice. Here it's a funny thing I can do. Suppose Alice performed a measurement. Okay? And suppose Alice finds, suppose this is the singlet, say up, down, minus down, up, in the Z basis, and suppose 1 over root 2, this is my singlet, and suppose Alice performs there a measurement of Z, and she founds up Z. Then this state decays to 1 over root 2, up Z, down Z. If this is Alice's particle, and this is Bob's. Now that is the same, so this happens if Alice measures and she finds up Z. If Bob measures and finds down Z, exactly the same thing happens. So if you just look the ordinary quantum mechanics, it doesn't matter who performs the measurement. Alice or Bob, the state decays simultaneously in these two locations, and that's all it is. Singlet propagating, do you see? Again? Okay, singlet propagated, and then it decayed. Let me look at that image. Well, if Alice performs a measurement, whoops, Alice disconnects the thing here. And this state is up Z, going forward in time, and this is down Z, going backward in time. This happens if Alice measures sigma Z and found it plus 1. Nothing happens on both sides. Nothing. On the other hand, were Bob to do that, Bob would disconnect it, and nothing would happen on Alice's side. So who is the one that performs the collapse? Sorry, there is important. Is not the same thing. While ordinarily quantum mechanics will tell you it's exactly the same thing. What does it matter who collapsed? Well, it does matter. Now, how do you see that it does matter? Because here, the spin, what is about measure Z? What about the spin x here and x there? Are they connected? No. The spin in the x direction here and there are totally disconnected because I cut the connection here. So if I were to measure here, also say between this time and that time, sigma x minus sigma x, I would find sometimes 0, sometimes plus 2, well, plus 1, sometimes minus 1. The spins are cut. For sigma plus 2, minus 2, or 0. While here, around this time, I would find sigma x minus sigma x equals 0. Now, you can obviously do that in ordinary quantum mechanics, and you run down, and you have to run down the equations, and you have to say how I perform this measurement of the difference of the spin between two times without measuring each of them separately. And whether I do it on Bob's side or I do it on Alice's side, I would find something completely different. Okay? But that is the price you have to pay if you do ordinary quantum mechanics. While here, after I set up this thing, I see it immediately. Okay? So that's why I like it, and I believe that it has a lot of potential. And now, because I understand that the best way to escape being asked questions is to talk more, let me just give you a funny thing that you can do with it. Here it's an interesting one. Forget Alice and Bob. Just don't ask me questions about Alice and Bob because I will have to. Okay, let me not do that. Here it's an interesting one. This moment is fully connected with this supposed ordinary time evolution. Maximal entangled with that, this maximal entangled with that, and so on. Let me show you a particle with a double life. Let me disconnect this and say here I prepare some other state, psi prime. Now this one, let me maximally entangle with where? instead of going back in time, I want to connect it here. This one, I want to connect it there. This one, I want to connect it up. Sorry. What do I want? This one, yeah. First of all, this one, I want, okay. I want to connect not every second one, but every one like there. And this one has to be connected here.
Sandu, can I tell you what I want?
You want a triple life?
Show me how you do that before we...
Oh, I just connect every second.
How do you connect?
I draw lines. Look, if you ask me in reality how you want to have a double life, look, I don't want to enter in any family problems. And, no, don't ask me suggestions like this. But look, the standard thing is that I have a state here, and this I entangle with the next one. But the next one will be there. So entangle. This one I entangle with the next one that is up here. So this one I entangle there. So this state psi propagates on those moments of time. Now here, I have some other things. A state here that is psi prime. This guy here is entangled to the next moment of time. Here, this one is entangled to its next moment of time that is there, and so on. So on the same particle, you have a psi and a psi prime. It has a double life. Depends on which moment of time you measure, on odd or on even. I've never seen that in nature.
Oh, you have never?
Not yet.
Oh.
Look, don't ask me to tell you. Maybe people have double lives. Who knows? Here I do that at these moments of time. And you can get something that has triple lives. Okay, you can play games, and this offers you a new way of asking about interesting physical connections. Now this is not ordinary time evolution, because here in the same particle, at various moments of time, has various things and various time evolutions. Perhaps if you perform a measurement, you see the measurement that I made here and that cut this. By the way, were you able to see from that side? Mm-hmm. Yeah. So those were really the absolute instantaneous measurements, the one that really cut 2 moments of time. On this scale, probably what we call a strong measurement, it's much longer, so may average over moments of time. So I don't know exactly what I will get for a particle with double life if a measurement is over longer time, some sort of interesting average.
Sandu, I mean, here you do it in time, but you could also imagine a chain in space of teleportation, just on a quantum network, where you teleport in space.
Look,
and then you should have an analog of that.
Look, there can be no better signature of the fact that this is a good idea than the fact that you can come and ask interesting questions about it. So yes, definitely. Okay, well, thank you very much for your active